Bruno Toaldo is an associate professor of probability at the Department of Mathematics, Giuseppe Piano, University of Turin. Born in 1985, he earned his PhD from Sapienza, University of Rome in 2013. Toaldo's academic journey includes a tenure track, University of Turin, and Junior University of Naples researcher positions, along with postdoc fellowship, Sapienza, University of Rome, primarily focusing on probability theory, non-local operators, and semi-Markov processes. He has served in numerous scientific and editorial roles. His research interest extends to modeling aspects related to anomalous transport, diffusion, and applications in mathematical finance and neuronal modeling. We are very happy to have you here. You may please proceed with your talk.
Okay. Good morning, good afternoon to everybody. Thank you very much, Pavan. Thank you to Arran and to all the organizers of this very nice series. Thank you to all the people which is connected and listening to me in this very, very warm afternoon, at least in Italy. So I think it's now the moment of mathematics. So what I want to do is this in this warm afternoon is to give you an overview of what is my point of view in the study of non-local equation, which is of course based on the theory of semi-Markov processes and time changes. When I say of course, I mean of course because there is in the title of the slide, not because it's obvious, but it's only one possible approach, but it's my favorite. So I want to give an overview of the theory. So I will avoid very, very technical details. I prefer to gives you what is the meaning of what I am doing. And since semi-Markov and non-local equation are, of course, an extension of classical theory, let me take just maybe 2 minutes for very, very basic facts on Markov processes, and then we move on. Okay, so classical theory that it is taught to MSc students says that if you have a family of operators on the space of continuous function vanishing at infinite, which is denoted here by C0, and then you take a family of linear operators on it, which is linear and that form a semigroup, which means that they satisfies 1, 2, and 3. 3 actually is just strong continuity, which means uniform continuity because this is the uniform norm. Then you can always say that this family of operators can be written in this way. It means that the transformation of a function u through the operator capital T is the expectation of the position of a Markov process that starts at x. Okay, so the vector variable is the starting point. And then you can associate a generator to this family of operators by computing this limit on the domain. So this limit is a strong limit. And then the theory says that this mapping, which is in practice the evolution of the average position of our Markov process, is the unique solution to an abstract Cauchy problem, which is this one. So this is Feller theory. Okay, so these are Feller semigroups, and the processes that are associated with the semigroups are called Feller processes. And they have the feature that they are strong Markov processes, and they satisfy, of course, some properties that can be proved by means of some classical theory. And one nice property of these Feller processes is this one. So if you define tau x to be this random variable, which translated in words, it just means that the time intervals between changes in the position of the process. Then this random variable has an exponential distribution. For any Feller process, there is no alternative. But exponential means that the parameter, which is of course position dependent, so it can depend on x, is not necessarily a finite number. It can be 0. And so when it is 0, the process never leaves the position x. It can be infinite. So if it is infinite, the process leaves the position x immediately. Or it can be, in the classical case, just a finite number, which means that the process stays in the position x for an exponential, in the classical sense, random time, and then it moves away. But it is even more interesting that failure processes, strong Markov processes, they cannot live continuously holding point. So if your parameter here, lambda, is finite, and so if the process spend an exponential time in the position x, it must jump away. It cannot move away continuously. This is this theorem. So in practice, this, together with some other properties, implies that if you want to look at the trajectories of failure processes that are connected to your Cauchy problem, then in practice you can observe step process. Step process means this guy here, Markov chain-like, or continuous processes that are never constant, or jumping processes that are never constant, or combination, okay, of this kind of processes. But what you will certainly never see is a failure process which is constant for a time which is not exponential, and you will never see a failure process which is continuous, and it moves away from continuity point. Sorry, it moves away from holding point. So from an interval of constancy, continues. Then just to understand what is going on, imagine that that this is your process. This random time here between the jumps are not exponential, and you want to check Markov property. So you condition to your trajectory. So you have the information up to this time s. Then inside the filtration at time s, you have a lot of information. But in practice, you can ignore a lot of things, in the sense that if you assume independence between the waiting times, then you can ignore previous waiting times. If you assume independence between the jumps, you can ignore the previous jumps, and this is okay. But why you can ignore gamma s, so the time passed since the last position? This is, of course, not true in general. This is true for Markov chains because the exponential random variable has the property of lack of memory. But in general, you cannot. And this is, in my opinion, the more intuitive way to start with the definition of semi-Markov process. So it is possible to say that this process here, xt, is semi-Markovian if it is Markovian together with this further information. Actually, it is strongly, this is the true definition requires strong Markovianity together with this further information. Then, if you want to rewrite the semi-Markov property, it is just a kind of Markov property because you just condition to your trajectory, and from your trajectory, you get rid of a lot of information, but you must take care of the position and of the sojourn time in the current position, which is gamma s. Of course, this is a function of xt. Sorry, this is a mistake in my slide. For any function u bounded and measurable. Okay, so this is very colloquial and heuristic, but let me give a couple of definitions. So the classical, in my opinion, more intuitive definition is the one given by Gihman and Skorohod in their book in 1975, and the definitions say that a random Cadillac process is semi-Markovian in the sense of Gihman and Skorohod if it is Markovian together with this further coordinate gamma t. Okay, so the sojourn time in the current position, the age, we will call this also the age of the process. Then a more general approach, which is inspired by the theory of Lévy, that used this approach to define semi-Markov processes, but only for step process, is then taken by Harlamov in his recent book and made more general in continuous time. But also other authors worked out before Harlamov. I'm speaking about Harlamov because it's one of the few book and references on semi-Markov processes. And these definitions say that a random Cadillac process is semi-Markovian if it has the Markov property when it takes it from open set. So if you have the information when it takes it from open set, then you can ignore everything inside this filtration. You can start the process when from the position when it exits the open set, for any open set. What is the idea here? The idea is that in practice, when it's a regenerative property. So when you exit from open set, your age, so the time that the memory accumulated by the interval of constancy disappear, because if you exit an open set, you are moving heuristically, okay? So your age is 0, and from that point you have no memory of the past. Okay, the relationship between the definition is that definition 2 is more general, so it includes more processes. Definition 1 indeed implies definition 2, and the converse is true only for step process. So this is just a picture. This is a picture because I was just wanted to show you how it looks like the trajectory of a semi-Markov process, which is not a step process. Okay, this is a sampling. We did as Enrico Scala told you some seminars ago. He cited my poster with my PhD student Sedeno Giron. We are working on this, and so this is just a sample picture. So we still don't have a published paper on the method on how to make simulation, but we are working on this. Okay, so now it's the moment to tell you what happens to the governing equation of a semi-Markov process. Okay, so we have clear ideas now what is a semi-Markov process. We want to establish the connection like with the Cauchy problem, PDE, like we had for Markov process. Of course, this is impossible because semi-Markov is very general object. So if you ask me what is the governing equation, can you write an equation that this function here satisfies for any semi-Markov process? Of course, I don't have an answer. It's too general, but there is an approach that we can use to give this answer, and the approach is based on time change. So using time change technique, I can give answers to these questions. And time change techniques in practice means the following: to construct a Markov process, to construct a semi-Markov process starting from a Markov process, we can use time change. And in order to do this, we need the following object. We need a vector with 2 coordinates, but the previous one can be more or less arbitrary, and the second one must be real valued, strictly increasing and jumping. Together, they must be Hunt process. If you don't remember what is Hunt, just Feller process, it's okay. Then we define the first passes time of the second coordinate in this way. So in practice, LT is the inverse of the second coordinate. And then we use this process to time change the first. And we have, okay, here I wrote 2 processes, X and X minus, and the difference is this minus here. Why I did this? Because in practice, M and sigma, they can jump simultaneously. And if they do jump simultaneously, then when you time change, LT is a jump time, can be a jump time of sigma. And if LT is a jump time of sigma, then you have to decide which value you want to give to the Markov process M. Probably I didn't say this clearly, but if they jump simultaneously, then LT, which is a jump time, that can be a jump time of sigma, is also a jump time of M, and then we have to decide the value that our process have. So we have to give right or left limit. So these 2 processes can differ. Of course, if M is continuous or if M and sigma don't jump simultaneously, there is no problem. But in practice, this can happen. And so we have to distinguish. This guy here is a quite well-known object, and is semi-Markov according to both definitions. This guy here is almost semi-Markov in the sense that the proof is not complete. We are working on this. I'm working on this with Giacomo Ascione, and we are still working on epsilon and delta. We think it is semi-Markov, but it has. We already know that it has a semi-Markov property in a weaker sense than the one I told you before. I will be more precise later. Another thing one has to be careful is that this guy here this x minus is left continuous. Okay, so one has to modify it to be right continuous and then study the semi-Markov property in the right sense. So what is the heuristic behind all of this story? Just some picture to explain what I told you before in the easy case. So imagine that our first coordinate is just a Brownian motion like, okay? Then we have sigma, which is strictly increasing and jumping. When you take the inverse of sigma, you get LT, which is, if sigma strictly increasing, this is a continuous function, continuous trajectory, and it is constant. It has interval of constancy induced by the jump. Okay, so the length of the jump of sigma, this jump here, are interval of constancy in the inverse process. So now we take M, we do the composition between M and L, so we do this operation. When we compose continuous function, we get continuous function. So the trajectory of the process X, which is the composition, are continuous, and they have, of course, interval of constancy induced by the interval of constancy of capital L. So in practice, we have a continuous process with interval of constancy, which moves away continuously from interval of constancy, and the interval of constancy can be arbitrarily distributed because they come from the jump of a Markov process. So in practice, they can have any distribution. Example. So let's do some classical example from which we have already a theory, which is more or less known to all of us. So the very prototype of the theory is the case when the two coordinates are independent. So we take a Markov process, and sigma, we take an independent coordinate, and further we assume that sigma t is a subordinator. A subordinator is a strictly increasing Lévy process, starting from 0. Okay, actually it is a non-decreasing Lévy process, but suppose it is strictly increasing here, then subordinators are associated with a Bernstein function, in the sense that the Laplace exponent of a subordinator is a function f that has this representation. This is the Lévy measure. This guy B is the drift, and the set of Bernstein function is in bijection with subordinators. And then in practice, what happens is that the governing equation of the semi-Markov process. So if we take the expectation of our semi-Markov process constructed via time change, is this equation here, where instead of the first order derivative, there is a non-local operator that here I am generally denoting by f of d in dt, okay? Just to be general and heuristic. And but this is important because in practice, independently from the definition that you use here, you can always give the meaning to this operator as the Bernstein function of the first order derivative. You can use rule of calculus to understand this. But then there are different representations for this operator, and here there is a lot of classical literature to define this kind of non-local operators. Then, for example, if you just to mention something, for example, if you take a fractional power, so if the Bernstein function is the fractional power, so we are in the stable subordinator case, and the inverse stable subordinator, then this is the fractional derivative, and you can use Caputo derivative to define it. Then if there is a drift, then if the Bernstein function is complete and with no drift, you can use the theory by Kochubey. And in practice, you can take the definition of fractional derivative. You can put a kernel inside the fractional derivative instead of the fractional one. You make assumption on the Laplace transform. If you assume that the Laplace transform is tilted, then in practice you can associate a Bernstein function to this, and you are defining a non-local operator that has this meaning. Then there are other approaches, paper by Chand, that put explicitly the kernel here is the tail of the Lévy measure. But also another paper by Liu, Rockner, and Da Silva, they studied this kind of equation even in the nonlinear case, which is very useful because you can study this equation without assuming the initial condition in the domain of the generator. Then there is, inspired by Kolokholstov, we can use the generator form to define the operator f of d on dt. This comes from a paper by Kolokotst, a very old paper in 2007. Then you can use, for example, other techniques like inverse Laplace transform method. This is also done by Merschert and Scheffler in 2008, and then by Dovidio and Capitanelli more recently. So there are different techniques. The last thing I want to mention is that this can be a bit side remark. You can generalize this theory to the multi-parameter case. So in practice, this theory works if you take, for example, a b-parameter Lévy process, so associated with a multi-parameter semigroups, a bivariate subordinator with inverse defined in this way. And so this multivariate subordinator is associated with multivariate Bernstein functions that are defined in this way. And then you can, the authors of this paper that are Riafrate and Ricciuti, they realize that if you time change this Lévy, then you have a density. This guy here has a density that satisfies this equation, where these are the adjoint of the generator of the single coordinate of the semigroup. So it's a bit complicated theory, but in practice, this is a multivariate version of Bernstein function of this operator. So in practice, it's just a multi-parameter generalization of what I told you before. So there is, of course, a huge literature on this kind of operators and time change. A lot of people worked on this, not only the one I told you. I just picked some paper that I used in the past. But I want that it is important that this is the prototype of the theory, because it's easy, because there is independence. So independence between the coordinate of the time change makes things quite explicit and easy, just to let you understand what is going on. Imagine that your time change is a Markov process that has some transition probabilities P, okay? And your time change with an independent inverse subordinator. So you certainly know that with some conditioning argument, very easy, then the state probability of the time changed process are just the integral of the transition probability of the Markov process against the one-dimensional marginal of subordinator. So this is more or less explicit, okay? This is something you can deal with. But here independence is crucial. So if you time change with something which is not independent, then things are definitely harder. And I take the opportunity to advertise my recent paper with Giacomo Ascione and Mladen Savov, when we give this very, very precise information on this the marginal of inverse subordinator that are, of course, crucial quantities to study this context. Okay, now it's the moment to generalize the time change. So we don't want now independence, so we want to study something different. There is a general theory developed by Kolokotstov and people by his group. Here, I just pick one random theorem from his series of papers. They have several. In practice, they took this process, they used the generator of this process, and using the generator, they write the governing equation of the time change of M through the inverse of sigma. Here is just one of their statements. For example, here you can see that in this equation, there is a kernel that it's dependent on the integration variable. So in practice, this guy here is related to the jump kernel of this process, sigma. So in practice, we are in a non-homogeneous setting in the theorem I wrote here, but they have different statements and more general. But the idea is this: using the generator, you can write the governing equation of the time changer process, even if it is not very explicit sometimes. There is another approach based on continuous time random walk limit, which is also very general in this paper in 2017 by Baumer and Straka. More recently, instead, coming back to independence, here, okay, I'm not cheating, I'm coming back to independence, but for a nice reason, because there is a recent paper by Pierre Paty where they studied the time change of M through the inverse of a process sigma, which is independent, so the inverse of the second coordinate, but again in the independent case. But now sigma is not a subordinator, but it is just a non-decreasing self-similar Markov process. And he realized in practice that the governing equation using techniques from self-similarity has the very, very same form as the Caputo derivative with the kernel, which is computed in exponential of minus y. It's the tail of a Lévy measure of a subordinator, which can be associated with the Lamperti transform to the process sigma. So if you are familiar with the theory of Lévy processes, you know what I mean. Otherwise, it doesn't matter. The point is that the structure of the equation is the very same. There is just a kernel which can be associated with the tail of a Lévy measure. And the theory works in L2 in their paper. It is not pointwise theory. One of my favorite time change instead is the state-dependent case. The state-dependent case is very nice. There are morally, there are two approaches to study the state-dependent case. The state-dependent, I mean, for example, that the fractional derivative, the order of the fractional derivative depend on x, the vector variable of the problem. One approach is use continuous time random walks limit, and this is done, for example, by Kolokotov several times, but also by Peter Straka. But here, I want to briefly discuss my favorite approach to the state-dependent case, which is based instead of Markov additive process, because it is easier to connect with Semi-Markov theory. So let me tell you what is the point. So take a Markov additive process. What is a Markov additive process? It is a Markov process such that the future is not dependent on the position of on the true position of both the process in the sense of the increment, of course, but from this conditional expectation, you can remove this coordinate. So this is the classical definition given by Similar. This is very general, okay? If you use this definition, you find a big class of processes. But to deal with what I want to do, we can further suppose that the second coordinate is just like a subordinator, but it is not a subordinator because it is not independent of the first. But suppose that this coordinate behaves like a subordinator with a Laplace exponent, which is given by a Bernstein function, but the Bernstein function is parametrized. And this parameter is occupied by the position of the first coordinate. So in practice, depending on the position of the first coordinate, this sigma behaves locally like a different subordinator because it changed the parameter here. And then we consider the time change, okay? So this is what we want to do. But let me show you what is the idea behind this time change. So look at the left picture, the picture on the left. This is an example of Markov additive process. So we have a Markov process, the first coordinate, and the second coordinate behaves like a subordinator, which is chosen, the kind of subordinator, depending on the position of the first. Then the Markov process jumps, and this sigma starts to behave like a different subordinator, chosen according to the position of M2. And this is clear in the step case, but the process capital M does not necessarily have to be step, okay? You can take Brownian motion, for example, and thus this guy here behaves like a different subordinator depending on the position of Brownian motion. Okay, so what happens when we time change? When we time change, it happens that we have a Semi-Markov process, so we have interval of constancy, but now the interval of constancy are the length of the interval of constancy are the length of the jump of the subordinator. But when the subordinator jumps over the position t, it is sigma LT. When it starts the jump, it is sigma LT minus. So in practice, when there is the jump at time t, the jump depends on the position of the process at time t, which is exactly the position occupied by our Semi-Markov process. So this is to say this is very easily, that the distribution of this jump is state dependent. It's different depending on the position. And this is interesting because it gives rise to an interesting phenomenon, which is called the aggregation phenomenon. This is the governing equation, okay? I just, before switching to the aggregation, I just tell you what is the governing equation, which has this form. And in practice, it is the very same equation that we had in the classical time change, but now the kernel depends on the variable x. Okay, so this is not very interesting. It is complicated technically, but it's not so interesting. The interesting part is the aggregation phenomenon. This idea has been introduced by Fedotov and Falconer in one paper. Morally, what is the idea? The idea is that they observe that if you take a suitable continuous time random walk on a lattice with state dependence waiting time that are exponential with variable exponential depending on the position, then they took some scaling and they realized that this continuous time random walk after scaling is associated with, is governed by this equation, which is fractional equation with variable order. Then this, I tell you, this equation is nothing more than the forward version of this one. Okay, if you take this one and you put a second order derivative here, then in practice, these two equations are forward and backward. Okay, so they should be associated with the same process, just in the forward and backward sense. Then Fedotov and Falconer realized that this continuous time random walk that approximate something governed by this equation converge when t goes to infinity in this distributional sense to the region when the function alpha of x has the minimum. So this is why this happened, because if you have power law waiting time, depending on the position, then there is, when alpha x is small, then the tail of the distribution of the waiting time are very, very, very heavy tailed. And so the process is trapped in that region because it stays there for a very long time. But this is for continuous time random walk. But what happens in our case? What we did is that, what I did with my co-author, Mladen Savov, is to prove this theorem. So this theorem morally says, here, let me remember what is x. X is just the time change of a Brownian motion, where LT is the inverse of the second coordinate, and this guy here is Markov additive. It means that sigma here is a stable subordinator, depending on the position, is like a stable subordinator, depending on the position of the Brownian motion. So when the Brownian motion is in one position, the subordinator start with, this guy here behaves like a stable subordinator with order, which depends on this position. So what happens to the time changed process is that this process is trapped in one specific region in the sense of occupation measure. If you denote by alpha I the limit to infinity and alpha j the limit to minus infinity of this of the function alpha x, then it happens that the process x is trapped in any neighborhood of the region when this function alpha x has the minimum, which is capital A beta. Is trapped in which sense? In the sense of occupation measure, in the sense that this goes to 1. But in order for this to be true, the minimum value of alpha must be very small, must be sufficiently small. In practice, it must be less than 1/2 the limit values of the function. If this doesn't happen, then there is no aggregation, there is no trapping. And so the process is attracted to infinity, and we have result 2. Here it is strictly minus, strictly less, and here is strictly big. We don't know what happened in the critical case where it is equal. It was cumbersome computation, and we didn't. So what is the heuristic behind this? The heuristic is that in this case, so we have our interval of constancy. The distribution of the interval of constancy is position dependent, and the tail are heavy in the sense that they behave like S. The distribution as a function of S behaves in this way, -1. So when alpha x is small, is very small, the tail are very heavy. And if this alpha x is sufficiently smaller than the other region, so if it is less than 1/2 the limit at plus infinity and minus infinity, then there is aggregation, because the process is trapped. It spends a huge amount of time in that region, and it does not go away in this limit sense, in this occupation measure limit sense. Okay, this I can skip. Okay, so now I want to skip to another kind of time change, which involves non-local operators, but coupled. So they are non-local in both variables. Okay, so suppose that now the process, the Markov process we are considering to construct the time change is this guy. And this guy is constructed as follows. So we have a second coordinate, which is in practice a subordinator, but it starts from a position V, arbitrary position V. And then we let him start to 0. So we just take its translation, and we use this to subordinate the first coordinate. So this is a Markov process. It is possible to prove that this is Markov additive, according to the definition I gave you before. And then we use this to construct our semi-Markov process. So we make inverse of the second coordinate, and we time change. But then I put here the minus. Why the minus? The minus is here because look at this process here. This process here, imagine that M, for example, is just a Brownian motion. Okay, so there is no jump. So when you subordinate Brownian motion with this subordinator sigma 0, then you are introducing jump. But the jumps occur exactly in the same moment of the second coordinate, because it's the very same process. It's just a translation. So in practice, these two processes, this first and second coordinate, they really jump simultaneously. And so we have to take to pay attention to the value we give to our process after the time change. And here we put the minus. So this is left continuous. I know it's weird, but this is what we need. Okay, in practice, this process, we are, okay, of course it cannot be semi-Markov in classical sense because it is left continuous. But if you want, you can modify, you make it right continuous, and you could try to prove semi-Markov property, and this is in practice what I'm trying to do with my co-author Giacomo Ascione, but we still didn't finish the proof. So it is almost semi-Markov. But there is already a result when under some assumption on the state space. Okay, so if this guy here is in RD and it's a jump diffusion, then you can use the paper by Merschert and Straka, and you can say that this process together with this farther coordinate, which is nothing more than the age, okay, it is possible to see that this process here is just the Sujon time in the current position. So the one we need to have the semi-Markov property in the sense of Gihman and Skorohod. So this guy here has the simple Markov property. It is left continuous. The classical semi-Markov property in the sense of Gihman and Skorohod, so the strong Markov property of the right continuous modification of this is, of course, again, an open problem I'm working on. So it is almost semi-Markov in the sense that you can take this left continuous process and you can say that it has the simple Markov property. This is something you can say. It is proved by Merschert and Straka. Then let me speak about the trajectory of this process. So this is, in practice, a continuous generalization, a non-stepped generalization of continuous time random walk, of coupled continuous time random walk. Because if you take a coupled continuous time random walk, which is nothing more than a stepped semi-Markov process, in practice, what you have a process which occupies some position. So there is some embedded chain, if you want. And then this position is occupied for a random time. So this Tn, capital Tn and capital Tn plus 1 are jump times. So if it is possible in the theory of semi-Markov processes that this waiting time, this interval of constancy, and for the next jump are not independent. This is possible because if you can take care in your filtration, if you can use in your filtration not only the position but also this, then also this quantity, which is the age, then if you have a joint distribution for the interval of constancy and jump, you just update your joint distribution with this information, and you can compute probability of events in the future. So it's allowed in the theory of semi-Markov. So imagine that these are not independent. But this is step. So in the case of step process, it's very intuitive. But now let's look at our semi-Markov process X. So in practice, we were taking m and sigma 0, and we were time changes m of sigma 0 with LT. But if you want, you can also imagine that you are taking m and you are time changing m with sigma 0 of LT minus. It is more or less another way to say the same thing. So this guy here is the undershooting of the subordinator sigma 0. What is the undershooting? The position when the subordinator jumps over level T, where the position where the jump that let the subordinator goes over T start. So the trajectory of this process are done in this way. If the process is on the diagonal, then it has an interval of constancy, and then it jumps and it goes on the diagonal. And then then it is on the diagonal, it starts an interval of constancy, and then it jumps again on the diagonal. So when you use this guy to time change a process capital M, what happens is that imagine that this is your capital M. So this is Markov process, the black picture, the black line. So the red line is our time changed process. So we are on the trajectory of the original process. There is an interval of constancy of the undershooting, so we stay constant. But then the undershooting jumps on the diagonal, and when it reaches the diagonal, it jumps over the original trajectory. And the process goes in this way. So in practice, of course, the interval of constancy and the forthcoming jumps are not independent, because as long the length of the interval of constancy, of course, affect the jump because of the evolution of the original trajectory, capital M. Then what I can say about the governing equation for this time change process is the following. So this is also work in progress, but this is very progress. So I'm quite comfortable that the preprint will appear in the forthcoming weeks, let's say in August. So these are some technical assumptions, but you can practice ignore. The point is that if you take the semi-Markov process under suitable assumption constructed, as I told you before, then the governing equation is this form. So there is an operator here, which is you can interpret as Bernstein function of d on dt minus generator. And this generator here is the generator of the process capital M, that the one I was considering before. So what is the meaning of this? The meaning of this is that this equation is non-local in both time and space, because this is the definition of the operator. And P is the semigroup generated by G. So even if G is local, then this is non-local in both time and space. But non-locality now is coupled in time and space. And the reason is obvious, because if you look at this picture, then you have interval of constancy and jump, even if the original process is continuous. You have interval of constancy and jumps that are not independent, because, of course, because of this construction, and thus the non-locality is coupled, and it is in this way. Okay, now, what I told you up to now, in practice, is the story of Cauchy problem. So we were speaking about abstract Cauchy problem, and in sometimes the equations were considered pointwise. I have not been precise in my talk on this, but they were all backward equations, because what we were discussing up to now is this function here as a function of the starting point of a semi-Markov process. But now this is also the case, the typical case in the theory of Markov processes and semigroups. Okay, Feller theory of semigroups consider backward equation. This is the theory I described before in the first slide, and these are called backward because the vector variable of the Cauchy problem is the starting point. But the theory of Markov processes can be generalized to the forward sense. So if you take the equation described by the semigroup, then you let the semigroup and the generator to commute, that on the domain it is always possible. You use duality between function and measures, and in practice you have that formally the transition probability, when they exist, of the transition probability always exists, but the transition density, if they exist, of the Markov process satisfy a kind of equation in the forward sense. So in the variable x, where the function p is a distribution or a density, if there is density, and A star, capital A star, is the formal adjoint of the generator capital A. So in practice, morally, what happens is that whenever a transition density of the Markov process exists, then you can write a PDE for it, which is written in this way. Of course, this is not true in general. Okay, this is morally, in the sense that you should verify smoothness and regularity properties of this transition density. But provided the smoothness and regularity, which is not trivial at all, this is what you can do. For example, just to make things more explicitly, let's consider a Feller process, okay, in an open set, and then consider the process empty dagger, which is the Feller process, kill when it takes it from the open set. So you send it to a symmetry point when it touches the boundary, or where it jumps outside the boundary. It depends on the behavior of your capital M. Then morally, this when a transition probability exists, what you can say is that you have a forward equation. Okay, you have a forward equation and this is the density of the killed process, and you have a boundary condition. If the process is not jumping, you have just boundary. If the process is jumping, then you should put Dirichlet condition outside the domain. So things are quite tricky here. I'm putting assumptions under the carpet, but morally, this is what we should find. By the way, we have some recent development on this kind of process with my co-author Ivan Biocic, when the generator is the besting function of a Laplace. So why I'm telling you this? Because I want to tell you something about this, the counterpart of this forward equation for semi-Markov processes. Okay, so some classical results that are known are due and well described in the book by Han, Kobayashi, and Humarov in 2018. So here there is a well-done theory. In practice, they did they took a diffusion and also even something more general, but certainly a diffusion independent from a linear combination of stable subordinator, which in practice is again another subordinator. They took an inverse, they time change, and they proved that transition density of this diffusion in the forward sense satisfies this equation. Okay, so this is transition density, and in the variable x is density, and this is the adjoint of the generator of the diffusion. This is something known. But what we did with my co-authors, Giacomo Scione and Pierre Paty, is to study easier case in some sense, because we just took a Brownian motion. We studied this equation, but we put here the non-local operator under some assumption, the classical one. But the interesting part is that we studied this equation in the forward sense on a time-dependent domain. So in practice, we took a given boundary and we studied the equation on this open set. Of course, we put Dirichlet condition, but now the Dirichlet condition are not on the boundary, they are even outside the boundary, and the reason is that this operator, if we don't modify the definition, involves value of this function outside the open set, so we should put boundary condition even outside, so they are exterior condition. And then we put 0 also at the infinite boundary, and in an initial datum which is regular enough. So what we did with this equation is to prove well-posedness. So we studied existence, uniqueness, and continuity with respect to the initial datum. So uniqueness and continuity is in practice is pure analysis. Okay, so here I want to speak only about existence because it is based on a stochastic representation that makes use of semi-Markov processes. Okay, so what is the idea? The idea is more or less the same that we have in the Markov case. Even in the Markov case, what you do to solve this kind of equation using processes, you take your process on the entire domain with no boundary, and you kill it when it touches the boundary, and you hope that it has a transition density that satisfies the problem with the condition. And in practice, this is what we did, but here the equation is non-local, so we took the semi-Markov process on the entire domain, which is associated with the equation on the entire domain, which is time-changed Brownian motion with some inverse subordinator. So we took X in this way, and we defined X dagger to be the kill process. So we took a boundary, a function, a given function. We killed the process touching the boundary, we send it to a symmetry point, and we study the state probability of this process. What's the problem here? The problem here is that we cannot use directly the theory of time-changed Markov processes, because what we are doing here is to take a semi-Markov process and we are killing it when it touches the boundary. We are not making the time change of a Markov process directly, because in practice, the operation of time change and killing is not symmetric. So what I mean is that if you want to use, for example, the time change of killed Brownian motion, then this doesn't work, because if you take Brownian motion and you kill on the boundary and then you time change, then you are time changing also the boundary. And this is not what we want. We have a fixed boundary, a given boundary, deterministic function, and we want to kill our process there. So what we are doing is to time change the Brownian motion, and then we kill the process. So this is similar to what happens for subordinate Brownian motion, subordinate kill and kill subordinate Brownian motion. But in that case, the problem is jump. Okay, so Brownian motion has excursion, so the jumps make the two operation different. Here we have no jumps, so the problem here is just a moving boundary, because everything is continuous. Indeed, if the boundary is constant, then the time change and the killing is again continuous, is again symmetric. Okay, because even if you time change a constant, it's again a constant, so the boundary doesn't change. So what makes problem here is the moving boundary. Okay, so what is the strategy? The strategy is the same, more or less, that it is used in one of the possible that it is used for Markov processes. So one takes, we have a boundary, we take the state probability of the kill process that has density, you prove that a density exists, and then you prove that this density as this representation, where P is nothing more than the transition density of the process, which is free, unkilled. So in practice, since it is time-changed Brownian motion, is nothing more than the integral of a Gaussian against the distribution of an inverse subordinator. But this is more or less what happens in the case of Markov processes. So why? It looks weird that this holds for the semi-Markov case. In some sense it is, but if you assume that the boundary has a suitable behavior, then this is true. And the behavior is done by the following arguments. So if you have your increasing boundary phi t, then you can prove that when the process touch the boundary, then this random time is a Markov time for your semi-Markov process. So the semi-Markov process has the Markov property at that time. And thus, in this case, that representation is true. But we really don't want that this happen, okay? So we really don't want, for example, that the boundary decrease, and it is the boundary that touch the process when the process is constant. So in this case, we don't have Markov time. And thus, we deal with this problem only when the boundary is increased, okay, to avoid this. This is something we don't want. So once we have this, we can use that, we can use this representation for Q. P is the state probability for the free process until, and it satisfies the non-local equation on the entire domain for x different than y. Then, morally, using this representation here, what you do is the following. You apply the Laplacian, you move it here inside the integral, then you move it, you use here that it satisfies the non-local equation. You move, you change the order here of the non-local operator and this integral. These two arrows that I wrote down in 2 lines are more or less 15 pages to justify. So it's not easy. And then in practice, you have that in the appropriate sense, this kernel here is a fundamental solution to our equation. So, but here, what I mean with solution, so this kind of problem are quite new, so we had to give a notion for solution. And so in these last 2 minutes, I just tell you what are the notion for the solution. So we say that the function is a classical solution of our equation on the time-dependent domain if, of course, if it satisfies the equation, which is 5. But then it must be continuous up to the boundary. It must have 2 derivatives continuous. It must be C2 in X on the open set. The non-local derivative must exist, and it must be continuous. Then we say that a function is a classical solution to the problem if it is a classical solution to the equation as above, and it satisfies the boundary, this boundary condition, and the initial condition. Instead, we say that the function is a fundamental solution in the heat kernel sense. So if you take integrated, if this kernel integrated against a function which is continuous, which is C infinity, sorry, with compact upper, then the integral is a classical solution. Thus, this quantity here converges weakly to the Dirac measure, so the starting point of the process. With this at hand, we have this rigorous statement, which is taken from our paper. So if you take a function, an initial condition which is continuous with compact support, you study this equation, then the unique classical solution is the integral of the state probability of our killed semi-Markov process against this function, which is what it was expected. Then here I have some other statements, but it is just technical details, so I will skip, and I will, here there are 3 pages of references that I also skip, because then there is YouTube videos, so I think that for now it's enough, and thank you for your attention.
Thanks, Bruno, for the nice talk. I ask the members of the audience to kindly raise your hand for the questions. I will read out your name. I will call out your name as they appear on my screen. Okay, I do not see any raised hands, so I assume there are no questions. Are there any final remarks or closing remarks from anyone? All right, probably no. So this is a good point to stop here. Thank you very much, Professor Toaldo, for this nice talk. It was very nice having you.
Thank you, Pavan. Thank you to everybody. It's a very nice opportunity for me to give this talk. So thank you very much.
The pleasure is ours.